When studying biology, the first thing you need to understand is a little bit of organic chemistry with how chemical bonds form. So atoms make up everything, and atoms are made of three types of particles: protons, electrons, and neutrons. Protons are positively charged, electrons are negatively charged, and neutrons have no charge. The core of the atom is a nucleus. It's made of protons and neutrons. The number of protons defines the identity of the atom. The number of electrons can change, the number of neutrons can change, but if the number of protons change, then the atom becomes a different element. Electrons are not in the nucleus, instead they orbit the nucleus in what are called shells. The first shell can hold 2 electrons, the second shell can hold 8 total electrons. By default, the number of protons is equal to the number of electrons for an atom. The number of electrons can change, but only through chemical reactions. The outermost shell is called the valence shell. So here's hydrogen as an example. Hydrogen only has 1 proton and also only 1 electron by default. The first shell can carry at most 2 electrons. So now we look at oxygen as an example. Oxygen has 8 total protons and also 8 electrons, which means that 2 electrons go in the first shell and the other 6 will go in the outer shell. That outer shell can carry 8 total electrons, but there's only 6 because oxygen only has 8 electrons. So the second shell can carry at most 8 electrons. So this is the octet rule, which means that every atom wants to have a filled valence shell. So as you can see here, we have all these atoms without filled valence shells are clamoring to be like the atom with a filled valence shell. They all aspire to be the atom in the middle, and they'll fill up their valence shell by trading electrons through chemical reactions. So hydrogen by default only has 1 electron. It wants to have 2 electrons because that would fill up its valence shell. Oxygen only has 6 electrons in its outer shell, so it wants to gain 2 electrons to fill up its valence shell. So how they do this? Through chemical bonds. So the octet rule states that atoms are unsatisfied if valence shell does not have the maximum amount of electrons that it could have, so they're going to undergo reactions to get their valence shell filled. So what are our 2 types of chemical bonds they can form to do this? One of them is the covalent bond, the second one is the ionic bond. So covalent bond means that electrons are shared. So in the case of water, 2 hydrogen atoms will bring their only electron over to oxygen. Because oxygen wants 2 more electrons, it'll take those 2 electrons and share it with the hydrogen. Because hydrogen also wants 2 electrons, 1 more extra electron. So oxygen will give 1 electron to hydrogen, hydrogen will give 1 to oxygen, and then they share those 2 electrons amongst them. So in this case, everyone's happy. This doesn't really work with humans because humans don't share things very well. But in covalent, this does work with atoms. However, this only works if atoms both want to gain electrons. So covalent bonds are the most important type of bond in biological systems. Carbon, one of the most abundant elements in organic compounds, forms covalent bonds with itself and other elements to form the backbone of much of organic life. So carbon, it forms covalent bonds with itself, and that forms like the mass, like the stuff that makes up organic molecules, stuff. So ionic bonds are not when electrons are not shared. Instead, they're just traded. One takes an electron from another one. In this case, we have sodium and chlorine. Chlorine wants 1 extra electron to fill its valence shell. Sodium wants to get rid of its extra electron, so its shell underneath that will be filled. So that means its outermost shell will be filled. Okay, so the electron goes over from sodium over to chlorine. However, now sodium is positively charged because it has more protons than electrons because it just lost an electron. Chlorine is now negatively charged because it just gained a negatively charged electron. So now it has more electrons than protons. So what happens when a positively charged thing is going to be near a negatively charged thing? They're going to stick together, and that's what the ionic bond is. So this forms sodium chloride, which is another word for table salt. Okay, and lastly we have van der Waals forces. Van der Waals are not real bonds because they don't involve the transfer of electrons from one atom to another. So some examples of this are, one is dipole-dipole. The other type of van der Waals force is the London dispersion force. So dipole-dipole is, imagine we have a molecule and each side is different. Imagine our green squares are negatively charged and red sides are positively charged. So because all the negative is on one side, all the positive is on another side, that means that the positive side will only attract negative particles, and the negative side will only attract positive particles, right? They're totally different. The charges are on opposite ends. So one example of this in the real world is water. So water, we have two hydrogens bonded to an oxygen, and the oxygen is a very electronegative, which means that it has more protons than those hydrogens. So it's going to want to, that positive charge from all its protons is going to attract all the electrons. So it's hogging all of the electrons, and electrons are negatively charged. So that means that oxygen will be negatively charged relative to the hydrogen. The hydrogens are having their electrons pulled away by the oxygen. And the way we write this is with the Greek letter delta, and then we just write the charge to show that there's a dipole going on in the molecule. And dipole forces are permanent. They're permanent dipoles. So when water is in a solution with itself, it can form a strong connection with other water molecules, where the hydrogen from one water molecule is attracted to the negative end of where the oxygen of another water molecule. This is called hydrogen bonding, even though it's not a real bond, because electrons are not being traded. They're just being attracted one side of the molecule to another side. So hydrogen bonding allows water to have a very high boiling point. It allows water to have a strong surface tension, and it allows water to have a high heat capacity. And this is just because water is able to associate with itself, and that makes it so it's held together very strongly. So it's going to require some heat, a little more heat than usual, to break it apart, or it's going to require more force. If you're going to break it apart with physical force, it requires more than that than you would expect to break those water molecules apart. Okay, and lastly, we have London dispersion forces. So imagine we take our Rubik's Cube example. Let's pretend that the red squares are still positively charged and the green squares are still negatively charged. But if we mixed it all up, so now negative charge is being mixed with positive charge, and altogether there's just no charge. So we're mixing it together, but then randomly we just solved the cube just by randomly moving it. So now we have the negative charge and the positive charge, but then we go back to mixing it, and now it's all mixed up again. There's no net charge. And this is what London dispersion forces are, because around the atom, the electrons are sort of randomly moving, and it could happen where the electrons just so happen to randomly be all collected on one side of the atom. That means the proton on the other side is exposed, and it's going to be positively charged and negatively charged where the electrons are. So imagine this on the left carbon tail, where we have the hydrogen connected to that carbon, and the electrons that are moving around the hydrogen all just so happen to clump up on one side. Now it's positively charged on the other end. That means that on the carbon tail on the right, those electrons are going to see that it's positively charged on that hydrogen, and they're going to be attracted toward the hydrogen. This creates a temporary dipole. However, it is temporary. So that means that those electrons of random movement are going to move back over to the other side, and that charge is going to go away, and they're no longer going to attract each other. London dispersion forces are only really significant with large molecules. If you're dealing with small molecules, you don't really need to worry about them. It's only when this little temporary dipole thing with those electrons moving can happen for like a molecule that's got like 100 carbon chains, and that happens on every carbon chain, then yeah, there's going to be a lot of areas where those temporary dipoles can form, but it's only when you have very large molecules.